Okay, next in this chapter, we're going to talk about orthonormal basis and the Gram-Schmidt process. That is a process to make you build an orthonormal basis out of any basis. Okay, so let's begin with the definition. Of course, the basis of vectors in Rn, I guess you more or less know what it is. It's just a basis where every vector is orthogonal to any other vectors, and that's orthogonal. And if you want orthonormal, right, uh, it has to be orthogonal to any other vector and has a norm of 1. Okay, so the normal version is really not very hard. Once you've got the vector, the way to normalize it is just to divide it by its norm. Okay, obviously. Right. Interesting question. Prove that any orthogonal family is linearly independent. Okay, maybe that's a nice one to start with. Let's say you've got a family E1 up E2 up to EP vectors, and they are orthogonal. Okay, orthogonal family. So that means any one is orthogonal to any other. So let's try to see if they are linearly independent. Lambda 1 E1 plus lambda 2 E2 plus lambda n EP lambda p EP is equal to 0. Can I find some values lambda I that are different from 0? I want to prove linear independence. So any ideas? So it's a techniques we're going to use several times, meaning what I'm going to do is multiply all these expression by, well, let's begin with E1. E1 transpose, okay? The row vector that I obtained from E1 by transposing it, right? That's something I can do. So I multiply on the other side by E1 transpose, and of course that's going to be equal to 0 because anything times the 0, that's, I remind you, that's the 0 of, if my vectors are in Rn, that's the 0 of Rn. So E1 transpose times 0 is just going to be 0, right? So, well, actually, what is that? That's just, I'm taking the dot product of my expression with E1, right? I wrote it with the matrix expression, but this is really the dot product. If I expand that, I'm going to have lambda 1 E1 dot product E1 transpose plus lambda 2 E2 dot product E2 transpose plus etc. is equal to 0, right? Matrix notation, lambda 1 E1 transpose E1. Okay, that's just the same thing, right? Plus lambda 2 E2 transpose E2 plus etc. up to the P vector. So lambda P E1 transpose EP. Sorry, that's not the dot product for this last that I was writing. So that's just EP. Okay, and that should be equal to 0. Here, that's 1. Right, so, and if I assume that all my vectors are orthogonal by pairs, what is that going to give me? Well, obviously, all of these are going to be zeros, except for that one, which is, of course, going to be 1 if my vectors, well, 1 or the norm of E1. Where it's more, I didn't say they were orthonormal. Okay, so that's the norm of E1 square, right? So what I get that lambda 1 times the norm of E1 square is equal to 0. And of course, all of my vectors are different from 0 because they are, they make a linearly, well, they have to be orthogonal, all right? So, and, well, 0 vector is orthogonal to any other. So let's assume that 0 is not in my family. I should add this to this question. Okay. So this gives me that lambda 1 is equal to 0. That's the only way to get 0. And then using the same techniques, I multiply my original expression here by E2 transpose and then by any of the EI transpose. That will give you the result with only the lambda I times the norm of the EI vector square. That should be equal to 0, and so lambda I is equal to 0. Okay, so that's it. You, of course, if they are linearly independent, I should have any orthogonal family, and the zero vector does not belong to my family. Okay, right. Um, all right. So next, still another definition, but again, this is the kind of things that probably you at least had an intuition of. We're going to have some standard basis, or other name canonical basis, or even natural basis in Rn. It's just the one that you know, it's the one that corresponds to the Cartesian frame when you're in R2, and just the most natural one, the one where you've got a 1 and all zeros for the vectors. All right, and of course these are obviously going to be linearly independent. All right, and they are orthogonal, and they are normalized, and that's just the basis that we will always want to refer to, because that's the one we know how to calculate with. All right, so our important theorem is the following one. If I have a linearly independent family in Rn, so I've got p vectors in Rn and they are linearly independent, then I can create out of this family another family. Okay, so my first family was called the U's, and I can create a family of E's where all the E's are going to be orthonormal. Okay, and the proof is very important. It's a constructive proof, meaning that we're going to see a process called the Gram-Schmidt process, and you have to be able to redo that on some specific examples. So next video, we're going to explain how that works.